Thank you so much for that welcome, and thank you all for being here. It's been a great conference so far. We've had a lot of great talks. So now you're going to be, comparing me to, well, all those other great talks that you've seen. So please be kind. So before I begin, I'm actually curious, how many people here in the room develop exclusively for Windows? All right, so for the people on YouTube, everybody rose their hands. It's great. How many people here develop at least some of the time for Windows? Okay, so that's a sizable group of people here. So that's great to see. So the time travel debugging tools that I'm going to be talking about today are Windows specific, so they only run on Windows. But I hope to keep the content of interest to everybody here, regardless of what platforms you're developing for. So if you develop for Windows, you'll be learning about some tools that maybe you can use in your day-to-day work. If you don't develop for Windows, then you can learn about some breadth about tools that are available on other platforms. So I personally, when I go to conferences, like most to go to talks about things that are completely unrelated to my day job, just to learn how other things work in the industry. So with that, this talk will consist almost entirely of demos, but I have a few slides to start off with to set the stage. So first, what is time travel debugging? So time travel debugging, or TTD as we abbreviate it and as I'll refer to it throughout this talk, is a reverse debugging toolkit. So what that means is you can use it to record execution of a program as if you were recording a movie of everything the program does. And this recording is stored in a trace file. You can then open that trace file in the debugger and replay it forward and backwards, just like if you had a DVD of a movie, you can fast forward and rewind through the movie. So with the movie, you might seek through it to find that great action scene that you want to watch a second time. With a trace of a program, you might replay through it forward and backward, trying to find where a bug happens so you can go and remove the bug from your program. In addition to being able to seek forward and backward, though, you can also query the contents of a trace file as if it was a sort of database. And so I'll be getting into that in much detail in the second and third examples that I'm going to show. But for now, just know that this can make pinpointing a bug far easier. So why time travel debugging? Why would we want to use this tool? So there's a few things I want to note just about debugging in general. So first, debugging is time consuming. So I'm sure that many people here are familiar with the tedious experience of carefully single-stepping through a function because you don't know exactly where the bug is or where the bug is going to happen. And so you don't want to accidentally step over it and then, oh no, you've got to go and start over from the beginning again. Second, debugging is hard, right? So, of course, most problems that we debug, like 90% of the problems we debug, are probably really simple things that, just little things that come up during development. But most of the time that we spend debugging is spent debugging like really hard problems or problems that are not, just, oh no, I, accidentally forgot to add something to a vector or something like that. And so, time travel debugging can be used for both of those kinds of problems, but it really shines in those more complex cases. So we also observe that debugging is already complex, right? We have these very specialized tools that we use, debuggers, to help us with this process. And so with TTD, we don't want to make the process any more complex than it already is. We want to leverage the existing concepts that you have with debuggers. So with TTD, we've worked to make the experience as similar as possible to when you're debugging a live process. So things like breakpoints or single-stepping or running the program, they all work similarly with time travel debugging. Now, we also have some time travel debugging specific capabilities, but we've tried to make them as similar as possible. Finally, so debugging may require multiple repros, and there's actually two different things to look at here. So first, you might have a bug that doesn't reliably repro, right? So it could be a race condition that only occurs once in a while and under particular circumstances that are hard to pin down. Or perhaps it's a bug that a customer hits reliably, but you're unable to repro it on your development machine or in a test environment. And everyone here is familiar with that joke bug resolution, or I hope it's a joke. It works on my machine, but that's not a good way to make customers happy, right? So that's not something we can actually use in practice unless you're a jerk, I guess. But second, even if the bug occurs reliably, and even if you can repro it locally, the repro may still be time-consuming to produce, right? So it may take you a lot of steps, manual steps of running your program and opening menus and dialogues, before you can even get to the point where you can run the repro. And this means you may have to repro it multiple times and do all of that work multiple times in order to solve the bug. Right? So for example, if you have a crash, you might first replay the whole thing until you get to the crash, and then you'll inspect the state of the program to try and see, well, what is the current state? And then that'll give you a few clues. So maybe the bug happened back here. So you'll set some breakpoints, and you'll go back and you'll restart and you'll rerun the whole repro and get to those breakpoints. And then it'll give you some more clues, and then you'll go back to the beginning, and you'll do this a few times iteratively. And so this can be very time-consuming. Like, I'm sure we're all familiar with the experience also of binary searching for a bug, right? Where you stick a breakpoint in the middle of a function, and you run, and you say, did the bug happen? Yes, okay, then you stick it halfway up. Otherwise, you stick it halfway down, and you resume. And so this problem can be very time-consuming as well, because every time you need to set the breakpoint earlier, like, you have to restart everything that you were doing. So with time travel debugging, you only need to record the bug happening once, right? So once you have a trace file that contains the bug happening, like, that's all you need. You can replay the trace as many times as you need. You can seek forward and backward in time as necessary to determine the root cause of the issue. And this makes time travel debugging a tremendously powerful tool. So a little background, some key features and information. So where did these tools come from? So time travel debugging originated as a Microsoft research project a bit over a decade ago, actually. And it's been used internally within Microsoft for all that time, mostly by product support and then by some teams that work on some of our more complex software products. A few years ago, my colleagues, decided to polish the tools and get them into a state that we could ship publicly, right? Like, our product support engineers, are willing to use, a more rough-cut tool than, we can actually ship publicly. Like, there's fewer of them, so when they have issues and they need to come talk to us, it's a lot easier than if, everybody in the world is coming to us, oh, I need help with this thing. So then last year at CPPCon, we shipped the first preview of the time travel debugging tools as part of the WinDBG preview. So one interesting feature here is you don't actually have to make any changes to your program. We can record basically any executable on Windows. All of the examples that I'm going to show you today are just built using the Visual C++ tools that you can download online. So there's no magic inside of your program. Everything is external. We just record whatever your program does. There's a few features here that distinguish us. So there are other reverse debugging tools in the market today that you can go and use. I don't believe any of them run on, at least none of them for C++ run on Windows. But there's a few things that distinguish our time travel debugging tools from those. So most notably, we're a multi-threaded and multi-core recorder. And what this means is we can actually record multiple threads running in parallel. And some other tools basically work by serializing execution as if it was running on a single core. So this can have a substantial impact on interactions between threads, and then of course it has a performance impact. TTD does not do this. We can also record programs that use shared memory or async I/O, so there's no issues with those sorts of things. And then we have these advanced capabilities to query trace data to get aggregate data of all of the things inside of the trace. So the time travel debugging process basically consists of three steps. So first, you'll record execution of your program. So you'll start your program with TTD attached, or you'll go attach TTD to the program, and this will produce that trace file. You'll then go and open that trace file in the debugger, and the first time you open it in the debugger is going to create an index file for the trace. So the trace is a very compact and efficient representation, but it's efficient for us to write. So we want to minimize our impact on the runtime of the program, so we're just going to write data in whatever is most convenient for us to do while we're recording. But it turns out that format is really not in any way convenient for the debugger to consume to do things like replaying forward or finding where breakpoints are hit or inspecting the contents of variables or objects. And so this indexing process basically takes the trace and it produces a second file that will help the debugger to do all of those things very efficiently. And finally, there's a link here, and I'll include it at the end as well. But here is, at this link, you can get all the documentation for time travel debugging, including whatever information you might need there. So how do we use TTD at Microsoft? So as I kind of alluded to before, we've been using it for a decade, and our support engineers rely heavily on it when working with customers to reproduce and resolve issues in their customer environments. Right, because we don't want to have to send an engineer out with a debugger to go and
debug Exchange server running on some customer's installation. Like, that would be very disruptive to the customer, and it would be very expensive for us. So our product support works a lot with this.
Additionally, internally, many teams rely on time travel debugging. So difficult to repro bugs, if they have a trace attached to them, they're much more likely to be resolved very quickly. And there's actually some teams where, if you go and report a bug and you're like, oh, I did this thing, like their first response will be, oh, can you get a TTD trace of this so that we can actually investigate it? Because it's a surefire way to be able to debug it, right? Because you actually have a recording of what happened. And then here I've got a list, like the kinds of places where we found time travel debugging to be most useful are those cases that I mentioned previously, the hard bugs, inconsistent crashes, memory corruption, race conditions, resource leaks, improper API usage, and then, of course, bugs that only repro on customer machines. So with that, enough talk. Let's do some examples. So first, I'm going to start with the basics. And so the first thing is, how do you get time travel debugging? So time travel debugging is part of WinDBG, and specifically it's part of the WinDBG preview, which you can get from the Microsoft Store. So if you have Windows 10 installed, you can just open up the Microsoft Store, and then there's like a search box here, and you search for WinDBG. You'll find this, and you click Install. So it's in the store, but it is a free download. Like, you don't have to pay anything for it. Though if any of you would like to pay a licensing fee afterwards, I'd be happy to take contributions. The one thing that I did find here funny is WinDBG is actually rated E for everyone. So we are very confident that you are going to find debugging so easy with these tools that there will be no need for any strong language. All right. So once you have WinDBG installed, and I have it installed on here, you're going to need to run it. And specifically, in order to record a program, you have to run with administrative privileges. You can't record a program unless you're running as admin. And what you're going to want to do is you're going to go to the File menu, and you're going to pick this Launch Executable Advanced. And you can see here in the little subtitle or link text there, it supports time travel debugging. And you can browse to find your program. So I've conveniently named it test.exe. And then you'll click this Record Program with Time Travel Debugging checkbox, and then this will tell it where to record the trace file, and this is fine. And then I'll click OK. Now when I click OK, the debugger is going to run the program, and it's going to record its execution. So note that the debugger is not actually attached to the program, so it's not like you could pause its execution and go inspect what's going on. It's just sitting there recording it in the background. And after the program finishes running, and if you saw it, it was basically just printing out a list of strings. So after it finishes running, the debugger is going to open up the trace file automatically, and the first thing it's going to do is it's going to run this bang index command, which will go and create that index for you. So you don't have to do anything. The debugger will do that automatically. And you'll see here it took less than 1/5 of a second to do that, because this is a really simple program. So then, when it's in here, you can now debug it as if it was a live process. And it starts off at the beginning of the trace. So right now we're positioned at the exact moment that we started recording execution of the program. And so this LDR initialize thunk is like a function that's very early during process initialization. So we could single step through to see what the program does. The first thing I want to do, though, is I'm going to open the source file for this program so we can take a look at it. Everything is a little cramped here. This is let's say it's substantially less cramped if you're not trying to make everything big enough to show up on the presentation. So this program here is kind of exactly what we might expect. So we have a local inside of our main function. We have a local vector. We then iterate over all of the characters from the letter A through J. We construct a string with that letter in it, just so we have some distinguishing thing. We print it, and then that's just going to print it to the console. We add the string to that vector of values, and then we sleep so that the program, we can actually see it working. So I'm going to stick a breakpoint just in the beginning of the function, and I'm going to click Go. And just like in Visual Studio, you can click on the gutter here to add breakpoints. And so what has happened now is the debugger has, remember we were positioned at the very beginning of the trace, so the beginning of program startup. So the debugger has actually replayed the trace. It's replayed all of the steps that this program did up until the point that it hit this breakpoint inside of main. So for example, if we look inside of the stack window, we can see we're currently in the main function, which was called by this C runtime machinery, which was called by the operating system. And if we look in the locals window, we can inspect all the local variables. So we can see the C hasn't actually been initialized yet, and then values is empty. So I'm now going to stick a breakpoint here at the end of the loop. And I'm going to hit go again so that we can replay forwards. And we can see now we're inside of the first iteration in the loop, and all of the local variables have updated to have their correct values. And if I click go a couple more times, we can see, again, the character is updated. Now we're in the second iteration with B. The values has 2 elements in it. And we can do it a third time, and so on and so forth. I won't do all 10, because that would be very boring. If you're familiar with WinDBG, all of the commands that you have used, you might have used in the past, also still work with this new WinDBG preview. And so, for example, I can use the G command, which will make it go until it hits the breakpoint again. And so now you can see we're inside of the 4th iteration of the loop with the letter D. So there's 2 things I'd like to point out here. One of them is that most features that work when debugging a live program still work with TTD, right? So we've been able to set breakpoints. We've been able to run the program. We could also single step or step through the program if we wanted to. We can inspect variables in memory in this locals window. But the second thing I want to notice, well, actually, the big exception there is when you're debugging a live program, you can actually modify the state of the program, right? So in here, we could change C to be, J, and then it would break out of the loop immediately. But you can't do that when debugging a trace because the program isn't actually running. Like, there's nothing for you to change. We're just replaying what's already happened in the past. So you can't, change what happened in the past. The second thing I wanted to note, though, is that when you're replaying a trace, we don't see the console window, right? And the reason for that is we don't actually replay any side effects. So here the side effects were our program had a console window and it printed certain output to that console. If you had a program with UI in it, we would not actually go and re-render all of that UI for you. If you programmed it I/O, we're not going to go and do that. If your program caused the computer to catch on fire and melt, but you managed to get the trace out of it before it completely melted, then replaying the trace won't cause those things to happen again. So that's just something to keep in mind when using these tools. So we've shown that we can replay forwards, but this is a reverse debugging tool, so we can also replay backwards. So you'll note that next to the flow control buttons, we have the normal flow control buttons to go and step out, and as you might be familiar with, we have these reverse flow control buttons. Now these are only enabled if you're in a time travel debugging trace, so I don't recall if they appear or not in a normal debugging, but you obviously can't use them when you're debugging a live program. So for example, I'm going to click go back once. And you'll see we've hit the breakpoint. But we've hit the prior instance of where we would have hit that breakpoint. So here we can see that the current character was D, and now it's C. And if we look at the values vector, you can see that the number of values was 4, and it's now 3. So it's basically we've gone backward in time to the prior time that we hit that breakpoint. Now, just like we could use the G command to go forward, there's a G- command to go backwards. So if we do that, we're now, again, in the immediately prior instance where we would have hit this breakpoint. So we've gone from C back to B. If you're familiar with WinDBG commands, then you might have used the P and T commands to single step the program. We also have P- and T- commands, which single step in the reverse direction. So those are the basics of time travel debugging. So I've shown, I've got a slide for that. Oh, no, I don't. So I've shown how you can record a trace of a program, how you can do basic navigation of the trace in the debugger, but this is a debugging tool, so maybe we should have a bug that we should actually look at. So I wrote a little program, as one does, to say hello to all of you. So hello to everyone at Pacific++. It's so nice to meet all of you. And then it has like this nice little UI that it pops up with a message box, and oh, I'm sorry, that's saying that the program crashed. This was happening earlier, so I recorded a trace of the program so that I could, go and debug it. But I forgot to do that, so now we can. I guess we'll do it live. So I'm going to open that trace, and once you've installed WinDBG, you can just, double-click. It associates itself with the run files, and I'm going to open it up. So since the program crashed, I'm going to guess that there was an exception that happened. Right now, it might not necessarily be a C++ exception, so perhaps it was a structured exception. If you want to know about how exceptions happen, how exceptions work in Windows, by the way, soon there will be a video posted on YouTube with a fantastic hour-long talk from CPPCon that I gave on how exceptions work on Windows. So I'd encourage you to go read that if you're or watch that if you're interested in more information on that subject. But anyway, so I expect that there's going to be an exception.
So I want to find out if an exception happened, and then if so, when. And to do that, I'm going to use a new feature of WinDBG. So it's in the WinDBG preview. It's been part of WinDBG for, well, at least a year now since we shipped it. But it's called the Debugger data model. So the Debugger data model provides a uniform way of getting information about the thing that you're debugging. So you can browse information using the model page up here on the ribbon, so you can actually explore it here. Or you can use the command window, and so that's actually what I'm going to do here. And so the way that you do this is you use the dx command. So this is the display, and then x just means something. And so this will display debugger data model objects. And I'm going to look at the current process. So this is like the root of the thing that we're debugging like right now, the current process that we're debugging. And in this case, since it's a time travel debugging trace, it's actually the trace itself. So we can see here the name of the process, and then this would have been the process ID when the program ran. So we're interested in event information, and so this would be TTD specific. So I'm going to click this TTD node, and this will allow us to browse through this data structure here. Like I said, we're looking for events. You can also get a list of all the threads and information about the threads. The lifetime is, this is the first valid position, and this is the last valid position. So these are time stamps, basically. So this is the lifetime, the minimum and maximum that you can set within the program. But I'm going to click events, because that's what I'm interested in, and we can see there's a whole bunch of them. So what there will be is there will be one event in here for every module load event. So every time a DLL is loaded into the process, we'll have a module load event. If you attach TTD to a process while it's already running, then you're going to have a long list of them at the beginning while we process the modules that were already loaded. There'll also be a module unloaded event, as you can see at the end after the program crashed, like we fabricated module unload events for those just so that we have a balanced pair. There's also events for every time a thread is created or a thread is terminated in the process. So you can kind of find the lifetime of different threads or find out when threads started. And then the piece that we're looking for here is there will be an event for every exception that happens. And this includes C++ exceptions, software-raised structured exceptions, hardware-raised structured exceptions, all the kinds of exceptions. So I'm going to click on this number 8 here to get more information about that. So we can see, OK, this event is an exception event. We can see the position, so this is that timestamp at which the event occurred, the timestamp at which the exception was raised. And then for the exception-specific data, we're going to have to expand this exception node. So this tells us that, OK, it was a hardware exception that occurred, so it was something that actually originated inside of the CPU. It has the exception code, so this code, C with lots of zeros and a 5, I know is the access violation code. So this means that we actually had a general protection fault. We tried to access something in memory in some way that we shouldn't have tried to do. And then it has the program counter. So this is the actual, the value of the instruction pointer where this exception was raised. So what I want to do is I want to go to actually this point in the recording to see what was going on. So I'll click this time travel button to do that. And this will, oops, wrong one. And this will take us, and it'll show us the, whoops, sorry, having some trouble here. This will show us the state of the program where the exception was raised. And, well, this is not very helpful, right? So the stack, it says, oh, you're inside of this, this function, but the debugger wasn't able to figure out what this pointer was pointing to, so it doesn't actually know what function that is. It doesn't know what your caller is. It can't find any local variables because, of course, it doesn't have the stack information. And if I look at the registers, well, two things stand out. One, here's that instruction pointer, which is where the exception occurred, and that's also what's at the top of the stack, so that's what's expected. But I noticed that the stack pointer and the base pointer are pointing to completely different locations in memory. So that should not happen on x86, right? They should be at least somewhere close to each other, since they should both be pointing into the stack. So my suspicion here is that we've corrupted the stack somehow. And what's happened is so someone corrupted the stack. They overwrote the return address of a function. We then returned, and when you run a return instruction, the processor will pop the return address off of the stack, and it'll try and execute it. So someone has gone and written this, this value over our instruction pointer, and we've ended up, in this bizarre state where the debugger can't find any information because, again, the whole state of the program is wrong. Now, if you had a crash dump, what you're looking at right now is exactly what you would see, and this is all you'd have. You could go and like poke around through memory and try and figure out like what's there on the stack, what has happened. But this is time travel debugging. We don't actually need any guesswork. We can just step backwards in time and see what happened. So I'm going to do that. So here on the ribbon, I'm going to single step backwards. So this actually, this first single step doesn't actually move the instruction pointer. So we actually have to fabricate a step for where the exception is raised, because it's like an exogenous thing that just comes out of the CPU. So this has taken us back to just after at the instruction that would have caused the exception. So I'm going to click once more. And now what we've done is we've stepped back over the return instruction. So now we're back inside of the main function just before we execute the ret instruction. And we can see that the debugger prints out what the next instruction is that it would execute, and that's the ret. So we can see here in the stack window that we're inside of the main function. And then if we look at the context, we can see the instruction pointer has been restored to what it was before inside of main. But we can see that the base pointer is still different from the ESP. The reason for that is the last operation inside of the function is it's going to go and update the base pointer to point to the right thing. So I need to step back once more. So we do that, and now we can see the rest of our stack. We still can't see our direct caller. Now the reason for this is we've gotten back to the point before we corrupted the CPU state, but we're still long after the point where the stack itself was corrupted. So the debugger is walking the stack, and it's not able to quite figure out what's going on here. So what I want to do next is I want to actually go and run back to see who was it that went and corrupted the stack on us, right? Who overwrote that return address? And to do that, what I'm going to do is I'm going to use a memory breakpoint. So what we can do is we can use this BA command, which is the WinDBG command, to break on access. So this breakpoint will be hit anytime a particular memory address is hit. We're interested in writes. We don't care about anyone who reads from this location. We only want to know who was the last thing that wrote to it. This is x86, so our pointer is 4 bytes wide. And then I'm just going to copy the stack pointer and hit enter. So that sets the breakpoint. Now I'm going to click go back and cross my fingers. And OK, so now we're actually sitting at the exact instruction that caused the stack to be corrupted. And so we can see we're inside of this common TCS copy S, so that's inside of the C standard library. I wrote some of that code, so I definitely don't think it's that. So we can look up one more, and we're still inside of the C runtime. So no, let's go up to the first thing inside of our actual hello program that we would have written. So there's a few things we can look at here, right? So this basically, I have this function, getPacific++ greeting. It takes a buffer and a size. It then has this message that we want to print inside of it. So hello to everyone at Pacific++. It's so nice to meet all of you. And then it just calls WCS copy S to copy the message into the buffer. And if we look, we can look at the local variables here. And we can see the value of message. So it has the whole message in it. And then we can see the value of the buffer, and we can see it just says, it's so nice to me, and then it kind of trails off. And the reason for that is we're in the middle of the string copy, right? Like we're in the middle of str copy, so it hasn't finished copying it. Now, because we know that this is the point at which we're overwriting, we're overrunning the buffer on the stack, I'm going to guess that my caller must have passed the wrong size in. And so if we see in here, the size, this function thinks the size of the buffer is hex 64, which is 100 bytes. And if I go to our caller, we can see, no, in fact, there's only 50 elements in this array that we're trying to copy it into. And it looks like the problem is I passed size of greeting, but these are wchars, and on Windows, those are 2 bytes, and so we're actually passing in 100 instead of 50. And so we've told it the buffer is too big, and thus the crash. So this test program was quite small, right? Like we could have debugged this problem very easily just by looking at it. Like if I were to close all the other windows, it would fit on one slide. But when the same kind of problem occurs in a gigantic code base, debugging it using traditional tools can be very tedious. Like I said, if you have a crash dump, all you see is the final state, right? Like you don't have some magical information of here was the prior CPU context before it crashed, and here was who wrote that data to the stack. So time travel debugging makes this process much simpler. So coming back to a little recap. So the key takeaways from these first pieces, I've shown how you can record execution of a process. We've seen how to do basic operations like stepping forward and backward and set breakpoints. We've talked about how replay is read-only, so you can't modify the state of local variables or other things while you're replaying. I've shown the basics of the debugger data model. We'll see some more advanced concepts from that in a little bit. I've shown how you can find events easily, so how you can actually go find where an exception occurred or where a thread started. And I've showed how you can use memory breakpoints. And one thing that I want to note about memory breakpoints is if you're familiar with using these, like CPUs actually have memory breakpoints, right? Like you can set a breakpoint where the CPU will break in, you stop execution of your program and let the debugger look at it if you write to some value. But the CPU is very limited. It can only, like on Intel, you get 4 debug registers, and so you can watch 4 addresses, and I think you only get up to 8 bytes that you can monitor. So there's really only like a very limited amount. There's no limit with time travel debugging. So for example, if you have like a 1 megabyte buffer, you can set a memory breakpoint on that entire buffer, and we'll stop whenever something in there is modified or read or whatever access you set on the breakpoint. Additionally, you can set as many as you want. So for example, if you have a std map and you want to know when any node is modified, like you could set memory breakpoints on all the nodes of your 10,000 element map, and that's not a problem. So those are things that you can't do with traditional debugging on a regular CPU. All right. So those are like the basics of how to use time travel debugging, right? So stepping, replaying forward, like everything that we've seen so far is quite similar to like what we would do in live debugging. There hasn't been anything that's particularly new. Like yes, we can step backwards, but like conceptually that's very similar to stepping forwards, replaying forwards. So time travel debugging also lets us look at code in a new and interesting way. We can look at execution of a program like as a queryable data source. So imagine you have a SQL database table. And each row in this table represents a particular point in time during execution. So the execution of a single instruction, right? So if your program executes billions of instructions, this table will have billions of rows. And this table has columns, and it'll have one column for each register in the CPU, so it can register the whole CPU state at the point that instruction was executed. And then it has a column for every byte in the address space of the process. So all 4 gigabytes for a 32-bit process, or I don't know how many gigabytes there are in a 64-bit process, but there's a lot. So it'll have all of this data, and so this table will be gigantic. But you could imagine having such a table, and you could imagine running queries over this to help identify like specific call patterns or specific memory access patterns and things like that. So we've actually enabled this sort of querying using time travel debugging. Another like similar thing to this, I don't know, has anyone here who develops for Windows used the process monitor tool? It's part of the sysinternals pack. Okay, actually quite a few people, that's great. So process monitor is another tool that records program execution, but in a very different way. It just records a program's interactions with the operating system, right? So registry accesses or file I/O or process creation, things like that. And in process monitor, like you can set a filter on it so that you can like filter it down to I just want file accesses by my particular program. And so you can kind of filter that information that way. So it's similar with time travel debugging. So, has anyone had this happen where it's 4 p.m. on a Friday and you're about to head out the door, you're just ready to go home, and you get an urgent email from your boss like this one? So my colleague, JRandom McHacker, is working on our new top secret media player for Windows, and we'll have to blank out this screenshot when we publish it on YouTube because like this is totally top secret. And the other Friday, he got this email from his manager, and it says, "I was trying out your program when I got this error." And then he helpfully included a screenshot with a message box, and the message box contains this dubious error message: "The operation completed successfully." So as everyone, I think a lot of people have seen this error message before or something similar to it. Right, so it was Friday afternoon. My friend really just wanted to diagnose this as quickly as possible so he could tell his manager what the issue was and head out for the weekend. He had a few options, right? So first he could ask his manager to send him, what are the repro steps? What did you do to make this happen? But like this could take several iterations, like maybe his manager would forget one of the steps, because it's really easy to forget a step when you're writing repro, writing up how to repro a bug. Or maybe it wouldn't repro on his machine. So like then they go back and forth and argue about whether it's actually a bug. And so that's not a great plan. That could take a while. He could go over and he could sit with his manager and watch his manager repro the bug on his machine. And my friend isn't really a big fan of having people like looking over his shoulder while he's debugging. And like it's always like, people are really impatient. Like if you're using their computer debugging something for them, and then like they're standing there waiting, like, okay, how long is this going to take? So he doesn't want to do that either. So he's a smart guy. He knows, time travel debugging is awesome. So he can ask his manager to send him a time travel debugging trace of the problem happening. And so that's what he did. He asked for a trace, and then he shared that trace with me, and so I'm going to share with you how he debugged this. So let's start by opening up the trace. I'm just going to close these old windows I had. Excellent. So we've opened the trace, and we're positioned at the beginning of the program again, just like we were before. And I'm going to guess that, he guessed, that his manager stopped recording when that pop-up appeared. So if we go to the end of the trace, the pop-up should still be on the stack. So I'm going to click Go. And I'm going to look at the stack, and I'm going to see, no, we're not inside of the message box call. Well, or we might be, because this is a multi-threaded program. It's got a UI, so of course it's got a lot of threads running in the background. So it's possible one of the other threads, actually has the message box on it. So what I'm going to do is I'm going to run this command called unique stack, and this actually works with live debugging as well. This is like a core feature of WinDBG. And what this will do is it'll print out all the unique stacks that are running. So if you've got a whole bunch of thread pool threads that are not doing any work, it'll just coalesce them all into a single stack, which makes it really nice to see like what is my program really doing. And then I'll just scroll up and see if any of these look interesting. And oh, here we go. Like this first thread looks like it is inside of message box. So our theory was correct. It's just the last instruction that we happened to record was positioned on a different thread. So when we went to the end of the trace, we ended up on the wrong thread. So let's look at this this function that we're inside of that's calling message box. So we can see it calls getLastError. So there's a common pattern with Win32 APIs that I'm sure many people here are familiar with, since most of you raised your hand when you said you program for Windows. But Win32 APIs tend to return a Boolean. And so they'll just say, yes, I succeeded, true, or they'll say, nope, I failed, false. And now, of course, I failed is not a particularly useful thing, so they want to share why they failed. And to do that, they set this last error state, which is a thread local variable, basically, and it has a more detailed error code saying exactly what went wrong. And in this case, because the error message that we got out of this was the operation completed successfully, I'm going to guess that it's not actually an error code in there. It's actually going to be 0, which is the operation was actually successful. So if we check, there's another WinDBG command called GLE for getLastError, and this will just print out the last error value for this thread at this current point in time. And indeed, yes, the current last error value is 0, indicating the operation completed successfully. So what this tells me is that we were running this program, and somewhere along the line an error happened, right? Because we identified that an error happened, and we ended up inside of this reportLastError function. But between the point that that error happened and we got here, we called some other Windows API that went and reset the last error state on us. So this is a common Windows API, like misuse is, you call a Windows API, it returns false. You're like, oh, okay, I'll need to get the information about why it failed later. Then you call some other Windows API, and it's like, oh, I'm just going to reset this, this thread local variable on you. And then when you do later get around to calling getLastError, like we do here, its value has been overwritten, and so you can't get to it. So what I want to do is I want to find the original error code, and to do that, we could go and debug step backwards and set a bunch of breakpoints, but there's a more interesting way to do this, and this is like one of the great things that TTD enables. And so what I want to do is I want to find all of the places where getLastError is called, right? So I'm interested in knowing. I'm also interested in knowing where they are in relation to the call to message box. So what I'm going to do is I'm going to use the data model again. So I'll use the dx command. And this time I actually want to store the result into a variable. So I'll just name my variable calls. And what I want to do is go to the current session which is, by the way, there's tab completion in here. So like if you're just poking around, you can just hit tab and kind of see what's there. So cur session is like the current debugger session. It's like one of the top level objects that we have. And inside of TTD, there's a calls function. And so this, we can actually pass it the names of functions, and it will go and it will find all of the places where those functions are called. So here, I happen to know that getLastError is inside of kernel base. And like I said, I'm also interested in where these calls are in relation to that message box call, right? So basically, I want to find the last one of these calls that returned an actual error before we ended up in the message box code. So I'm also interested in message box, so we'll do. OK, so this is the only operation that's going to take a little while. It's going to take 45 seconds on this laptop. And the reason for that is that it basically has to replay and has to stop at all of the places where these functions are called and gather a little bit of information so that it can give us a query. And if I open the task manager, you can see it's going to be very efficient. It's using all of our CPU power. So while it's going to take 45 seconds on my laptop, this scales very well across hardware. So for example, I have a 16-core AMD Threadripper at home, and it will use all 16 threads. Like even if the trace is of a single-threaded program, we'll still be able to replay across all of the cores and maximize utilization of your CPU resources. So we do a lot of testing across a wide variety of hardware, like to make sure that these tools are usable. So OK, it's done. So I guess it's probably done over here. OK, great. So, well, those results aren't particularly great. So these, basically, this returns an array. And so I'm going to add, whoops. So I'm going to add this -g to my command, which will print it out in grid form. And so, OK, well, like I said, this is a little easier to see when you have more than like 20 pixels across that this is, to make it fit. All right. So each one of these rows represents a call into one of those two functions that we asked about. And we can look through the columns of what we have here. So the event, it's a call event. We have the thread ID of the thread on which the call was made. We have the time start, which is the position. So it's the timestamp of the first instruction of the function for that call. The time end is the timestamp of the return, the ret instruction that was executed. We then have the name of the function, so we can filter on that. This query has two functions in it, so this is important for us to distinguish. The function address is just the pointer for that function. The return address is the address of the instruction to which control was returned after the ret instruction. And then return value is the actual value that was returned from the function. So this is, gives us some information. All right, so there's one thing also to note, and that is these are not returned in order. And the reason is we replay the trace in parallel across a bunch of threads, and we just collect the results as we get them so that we can give them to you. You don't always need them in sorted order, but for this one we do. So what we can actually do is the debugger supports something very similar to LINQ. Has anyone used LINQ in C# or one of the .NET languages? A couple people. OK. Well, it's not C# Pacific Sharp, so that's understandable. So basically, you can chain together operations onto the end of this to do filtering and transformations of the data. So here, I'm going to do calls.orderBy. Whoops, not quarterby, orderBy. Nope. And then this is going to take a lambda, and the lambda is going to be a C# style lambda, so it's very compact. So we're going to say for each element in here, we want to order by the time start. So that'll run. And you'll note that this is actually, this is quite fast. We've cached the results internally, so we don't have to wait that 45 seconds every time we go and filter this. And so now if we look at these timestamps, we can see, in fact, they are in order. Next, we can note that this last error value is thread local, right? So we're not interested in any calls that take place on a thread other than this main thread that we're on. So I happen to know this main thread is the thread with ID 1634. So I'm going to add a where clause, which will filter the elements. And then here we're just going to say we're only interested in calls where the thread ID is 1634. Great, so this has further reduced the results for us. Now the final piece of this that I'm interested in is I note that a ton of these calls to getLastError return 0, right? They return saying, oh, there was no error. So this just means that people were calling Windows APIs, and then when they checked to see what was the last error that occurred, well, there was no last error. So this will happen a lot. So I want to filter those out. So I'll add one more where clause. And we could coalesce these if we wanted to. It's just as I'm typing them in here, it's easier to do it this way. So I'm interested only in calls where the return value is not equal to 0. Or I want to keep the calls to message box, because again, I'm looking for one of these calls to get last error in relation to the call to message box. So for that, I'm just going to check to see, does the function name contain message box? Excellent. So now we've got our results. I'm going to guess that the results are actually kind of toward the end of this list. So I want to find out how many of the, I should note, it only prints out 100 results, and then you can keep clicking the ellipsis to have it print out the next 100 or the next 100. But I just want to be able to skip to the end. So what I'm going to do is I'm going to ask the debugger how many results are in this list. And for that, I need to get rid of the G. And I'm just going to append count. So this aggregates all the data and tells me how many elements are in this list. And, oh, well, that's in hex. I would kind of like to know in decimal. So in WinDBG, you can change the base using n. So now we've changed to base 10. And it will give us the result. All right, so there's 2,950 results. There's a lot of results in here. There's actually like a total of well over 10,000 calls in here. So we filtered out quite a few of them just using those filters that we had. So what I want to do is I want to go back to the query that I had. And I want to add skip, I don't know, let's just as a guess, 2,900. Let's say that we're going to hope it's in the last 50 that we're interested in. So this will skip all of them up to the last 50. I'm going to scroll up and see if I can find message box. OK, so here's the call to message box. And this call here, this call to get last error, was the immediately preceding call to get last error on that same thread that returned a non-zero error code. So if I time travel to this, this position, it's going to take a moment, and I look at the stack, yep, that's the threads. If I look at the stack, this is the stack at which we got that error code. So this is where that error code originated from, like the real error that we should have printed. And well, OK, this is inside of some operating system stuff. I don't know. I'm really only interested in what did our program do. So OK, this open file looks interesting. Let's look at that. And so here I can look at the local variables. And his manager tried to open a hilarious jokes text file. I'm glad he keeps them in a text file using our media player. So I'm told that you can't use the media player to open text files. That you should use. There's another Windows tool for that. Notepad. Yeah, he should use Notepad. So my friend can now go and tell his manager, oh hey, there's this other program you should be using here. And then he can write down. And then when he comes back in on Monday, he can go and fix why are we not printing the the right error message in the dialog. Excellent. So, key takeaways. So, it's really great when you can just tell someone, send me a trace of this thing happening. Trace files are fully self-contained, so we don't actually require anything from the system. So if you take a trace on one machine, you can just copy that trace over to another machine and replay it in the debugger. You do still need to copy symbols. Like if you had symbols, we don't include those in the trace file because the program won't actually touch symbols at runtime. But otherwise, it's completely self-contained. It doesn't rely on any of the system what's there. We've looked at the power of queries. So these enable like very novel and interesting ways of using the debugger. We've looked at how to filter using link. So I just showed a few of the the link options, but there's a whole bunch of additional ones. If you've used the link in C#, most of those are available, or at least a lot of them are available. And then I've shown you our new and upcoming media player app that I'm very excited about. I'm just kidding. That's actually one of the samples from the Windows 7 SDK. And we introduced a little bug into it so it would print the the wrong error code in it. And so yes, I also don't have colleagues named JRandom McHacker and manager McManagerface. Though that would be kind of cool, Not yet. I don't have people with those, not yet. Awesome. So I've got one more demo. So it's really hard to come up with demos for a talk on debugging, right? So Kate talked about how great it is when you're writing
when you're writing a talk, to really distill things, right? To get rid of unnecessary error handling and things, to make everything super simple, so you can just show exactly what you want to show people. You can't really do that for debugging talks, right? Like if I only showed you simple examples like that first example I had, you'd be like, okay, but does it work for real code? Does it work for real problems? But on the other hand, if I actually show you debugging real problems, a lot of times those require substantial domain expertise, or how does the program work, or things like that. So there's a fine balance to be found. So I was thinking really hard about what I wanted to show in the last part of this talk. And a little thing popped up on Facebook that it's been 5 years. 5 years ago, Kate Gregory and I taught a little introduction to C++ class, for people completely new to C++. And in the last part, we were going to show some demos of just, here's some things built with C++ to kind of encourage people to go forward. And I had volunteered, I was going to give this demo of using this library called Cinder, which is, it's a library, they call it for creative programming, so they do some graphics and UI stuff. And it's just a really cool library. It makes some things really simple. But I forgot about it. And so at lunch, Kate was like, oh yeah, remember that Cinder demo you were going to do? I was like, yes. So we had other demos to show, so that was good. But I realized, oh, I could do that here. I could finally, 5 years late, do that. So I was going through and I downloaded Cinder and I installed their, or I built their SDK. And I found in there's this little sample app. And it's basically just, they call it a visual, oh, okay, it doesn't scale. They call it a visual dictionary. And so basically, you can just click letters and then it'll restrict you, to, letters that'll actually spell out real words. And, it's just kind of a nice little app. Problem with this is, well, this is a debugging talk, and there's nothing wrong with that program. It seems to work fine. So what am I going to do? So I said, okay, I'm going to go and look at the source code. Maybe I can find a latent bug in there somewhere that I can show you how to debug latent bugs in apparently working software. Okay, well, while I was there, I found something really interesting. The sample uses std_list. Now, I've watched a ton of keynotes from C++ conferences, and if I know any one thing, it's you don't use std_list, right? You use std_vector all the time. There's no other container. That's the one you want. So I said, okay, well, before I search for a thing, I'll fix this, and I'll switch it out to use vector. So because I switched it out to use vector, it runs so much faster, right? I can, well, actually, the only thing it does faster is it crashes, because before it worked fine, and now it doesn't. So, okay, so I must have exposed some latent bug in there somewhere. So I'm going to go and, so I created a recording of this so that we could go and debug what's actually happening, what's going on in there. So I've opened the trace file that I had recorded earlier, and oh no. Yeah. Right? Can I go back in time? Can I? Oh, wait. Here we go. It flashed. Yes. OK.
We fixed it.
Problem averted. Yeah, I now know not to bump the HDMI cable. OK. Cool. So, all right. So it crashed. So I'm going to guess that an exception occurred somewhere in there, again, because that's generally what causes programs to crash. So we could go and we could look through that events list and go find the exception and navigate to it. But the debugger also, if you just click go, it'll stop anytime it hits an exception, just like it'll stop when it hits a breakpoint. And that's all configurable. There's debugger settings to do that. But I'm just going to hit go and see what happens. And sure enough, when I hit go, I can see it prints out, yes, an access violation occurred. Yeah, so let's look at what happened. So this move small function that we see here is it's part of memcopy, so I don't think the bug is there. I'm pretty sure that memcopy doesn't have any bugs in it, I hope. That would be terrifying. So let's just look at its caller, right? And so I look at its caller, and I see we're inside of, this is very hard to make all the things fit. All right, so we're inside of this char traits move function, and it calls, oh, I'm sorry, it calls memmove, not memcopy, but same thing. And I can see in here that it's going to pass, it's going to try and copy some number of characters from this first 2 buffer to this first 1 buffer. And I observe that this first 2 buffer does not look like a valid pointer. I don't know if anyone here is familiar with programming using Visual C++, but if you're in a debug build, and this was a debug build just because it's a little easier to show things, it goes and it fills all your local variables with this pattern CC so that you can identify unused local variables. Yeah, right. So this does not look like a valid pointer. But all we have in this function is the pointer, so I don't know where it came from. So we'll just look at our caller. So here we are inside of stdstring's assign function. And I can see we still have just the pointer, so that's not also giving us any extra information. So I look at its caller. And here we are inside of the assignment operator. I'm going to collapse this. The assignment operator for stdstring. And I can see that here is where we're calling assign, and we're calling it with the right-hand values data pointer. So I want to know where that came from, so I'm just going to expand the right. One thing I didn't note before is we do show, like, we pretty print all of the STL containers. We use the same NatVis native visualization format that Visual Studio does, so we, both debuggers work with the same kind of, pretty printing formatting that you can do. So I want to look in here, and okay, so I found the pointer. So this appears to be the pointer that's problematic. So I know a little bit about stdstring's representation. So I know that this bx thing is actually, it's a union. And so in here, like, stdstring has two representations, right? So usually in its normal case, it has a pointer to like some heap allocated buffer. But if you have a really short string, you don't want to have to go and like heap allocate. Like here, like I think it's a 1-character string, and so we don't want to have to go and heap allocate that. And so instead, it uses what's called the small string optimization to store the string internally within the string object. And so that's kind of what this looks like here, right? So we see this buff has n, the string n. And here in pointer, like, I don't actually know, so I can ask the debugger. You can evaluate expressions using this question mark thingy. And so if I ask it what n is, the hex value of n is 6e, so that's our 6e. And we can see, a 0 byte, and so that's probably the null terminator. And since this is on x86, when you display an integer, it's little endian, so all the bytes are in the wrong order. So what it looks like here is this stdstring, it thinks it has a heap allocated, it holds a heap allocated thing, but it doesn't. It holds, a small string optimized string. And, well, why is that? Well, the way that our stdstring implementation, decides which, what it contains is it looks at its capacity. And so if the capacity of the string is smaller than a certain amount, it's going to, that means it's a small string optimized string. If the capacity is larger than that amount, then it's on the heap. And so here we can see that the capacity, that's what this myres is 271. Now that's much larger than can fit in the small string optimization. We can only fit 15 characters plus a null terminator in our small string optimized storage. So that's, like, obviously, this is why it thinks that, this is why the string thinks that this is heap allocated. It's looking at the capacity and saying, all right, that's too big. So I actually need to switch to back to base 16, again, using n. So anyway, this is 10f, so that's important for everyone to remember. Don't forget that. So what I want to do is I want to find out, well, okay, how did this thing end up being 10f instead of, like, apparently it should probably be just f, right? If that's the maximum that we can store in the small string optimization. So what I need to do is I'm going to do what I did before. I'm going to set a data breakpoint on that thing. So first I have to find out where that thing is, and I'm going to do that using the dx command. And dx, like, it doesn't just take data model objects like that cur session, TTD stuff. You can actually also use it to describe variables or objects. So I'm going to explore for where that capacity is stored in here. I'm sure it's somewhere in here. This is all very complex because our stdstring implementation is very efficient, right? So it has, these unions and things like that. And okay, so I found the myres. So I want to find its address. And so what I'm going to do is I'm going to do this big complex thing that we did to get this string val type. I'm just going to add to it myres, and that will give us its value. Okay, no, that's not what we want. And so we'll just add in front of it an ampersand, because that's what you do when you want the address of something. And so that tells us here is its address. So just like we did before, I'm going to set a breakpoint, a break on access. We're interested only in writes. In this case, it's a 64-bit program that we were recording, so I'm interested in writes to this whole 64-bit value, 8 bytes. And then I'm just going to paste the pointer and set the breakpoint, and I'm going to run backwards. And here again, we can see, so this is the point at which we corrupted that value. So we can look at the code in question here, and it looks like, it looks like we're just setting a Boolean value, but somehow we're setting like the string. That's kind of weird. So if we look at this pointer here, or sorry, that's not what I want to look at. If we look at this, where this m should be deleted is in memory. So it's at this 364C0311, but we were expecting our capacity to be at that 364C0310. So that's interesting. So my suspicion here is that we've got a classic use after free, right? Like we had some object there, and then it was freed, and then the space was reclaimed for this, this other thing. And then later we came along and we had a pointer to the old thing, and we tried to use it, even though that pointer was no longer valid. So there's a few ways we could look at doing this. One way would be to start looking up the call chain and try and figure out how we got here. But I want to show you one of the other querying capabilities that we have inside of the debugger. And what I'm going to do is I'm going to look up all of the places where we wrote to this address. So what I'm going to do is I'm going to do dx-g again, just like we had before. Cursession.ttd, so this gives us all the TTD objects. And I'm going to ask it for memory. And what I'm going to do is I'm going to put in, oops, too many auxes. So I'm going to say I want all of the writes that occurred between this address and then an address that's 8 bytes further along. And I'm interested only in writes. So this completes quite quickly. So these are all of the locations, the 0x40 locations in memory, or in the program, where we actually wrote to that variable. I'm going to guess that it's something at the end that we're interested in. So indeed, we can see this second, the last one is kind of the first thing that pops out to me. I can see that we write 0xf. So that's kind of the value we expect the capacity to have, right? Because we know this is a small string optimized thing. And so if I go and time travel to that location, oops, we can see, yes, we're inside of the stood string constructor. So that's what we expect. But then the next thing that I notice is this last write. So it's a single byte write. You can see this is the size of the write, and this is the value that we're writing. So we're writing a 1. And we can see that the address that we're writing to isn't the 310, it's the 311. So it's 1 byte up. So if we time travel to that location, we expect to see the place, again, where we corrupted that value. And so if we time travel there, we can see, yes, that helped us find the set should be deleted. Now, I'll note that if we actually look at that location in memory, so, oops. Well, anyway, I forgot what I was going to type. Yes, that's what I was going to type. This is why I have notes, right? So if we look at that location in memory, we can see it hasn't yet been corrupted because this is the instruction that will corrupt it. And then if we single step using the T command, and then we look once more, we'll see now it's been corrupted. So we know exactly the instruction that it was. Now we found this earlier just by doing the breakpoint. I'm just showing off we've got this other feature in here where you can actually look at all the memory accesses, which is quite useful. And so if we step up into the caller, we can see that we're inside of this lambda. And this lambda is inside of this select node function. Thank you. Yeah. So the thing that I notice here, so this lambda, it takes a reference to a node, and that node is at the back of this container, this mdying nodes container. And I see that we're inside of a for loop, and inside of this for loop, we're also calling mdying nodes pushback.
So I think that my guess was correct, that in fact, the vector is being reallocated, and when it gets reallocated, we end up with this pointer pointing to now invalidated memory. But in order for this bug to happen in the exact way that it's happening, we actually have to end up reusing the same storage, just like at a different offset or different location. So I want to see, is that what happened? And to do that, we can actually see that inside of the memory accesses. So if we look in here, we can actually see these interesting patterns, right? So for example, here we have this long run of single byte writes where we write this byte CD over and over and over again to all the different bytes. And see, we write it to 310, 311, 312, and so on, all the way up to the end of the range that we're looking at. So the Visual C++ debug heap does this for you every time it does an allocation. So when it mallocs memory, it goes and it writes this fill pattern, 0xCD, so that you can identify, again, unused or uninitialized memory from the heap. And so if I were to actually click here, I would see, to see where this happened, I would see it's inside of memset, which is being called yes from malloc. So then if we continue looking through the other accesses to this memory location, we can see a similar pattern where it gets filled with Ds. So this is what the free function does in that debug heap implementation, is it goes and it fills it with Ds so you can identify memory that's being used after it was freed. And then later, again, we see CD, so it's actually being reused. So the heap is, again, going to return it from a new malloc call. And so if we click on one of these and we look at it in a little more detail and look at that stack and see where that delete is happening, we can see, yes, it's actually inside of that call to pushback, right? It is doing the vector reallocation. So we can verify that that's what's happening. So I guess it turns out I didn't find a latent bug after all. And the authors actually knew what they were doing in their program. So with std list, it's not actually going to move the elements around. So you can take pointers and it's no problem. But with std vector, every time you push back, it might reallocate the vector. So I guess the lesson here is I should assume that other people's code is beautiful, was one of the lessons from this conference. And maybe, assume that other people knew what they were doing. Cool. So just wrapping up a bit, time travel debugging is awesome. Like, we've seen some of the cool things we can do with this. All of these are still kind of toyish programs, but we use this to debug basically all of the most complex software products that Microsoft builds, including the Windows operating system, Exchange Server, all of the Office apps. Basically, everything that we ship has probably been debugged at some point in time using time travel debugging. You can download the WinDBG preview today. It's available in the Microsoft Store. Again, it's a free download, totally easy for you to try out. And you can find documentation here at akams/ttd. I'll now take questions that people have, but I'm going to preempt the question that I know is going to get asked, which is this in Visual Studio? And the answer to that is no, it is not in Visual Studio yet. They are working on integrating this into Visual Studio. I don't have dates or anything like that, but I can tell you that they are working on it. That's more than I was able to say at CPPCon last year, so that's good. Visual Studio, if Nick's here, I'm sure he can confirm 15.9, so either the most recent update or the next update to Visual Studio 2017 will have a new feature called snapshot debugging. So this is not time travel debugging, but what it does is basically every time you stop into the debugger, so like you hit a breakpoint, it'll create a snapshot of your program. So you can actually, like, if you then run your program, you hit another breakpoint, you can go back in time to see what the state was there. So this is not full time travel debugging. We don't record they don't let you replay every instruction that gets executed, but it's it's still an extremely useful feature. So that's something that people should check out when when that is released. Nick, has that been shipped yet?
That's a great question.
Yeah, that's a great question. Awesome. So ask him after the talk on that.